Thermal oxidation of silicon is a method where silicon dioxide is grown on silicon samples in a thermal oxidation furnace. It is generally a fairly simple process. An important fact to understand is that thermal silicon oxide layers are grown. There are other thin film technologies like sputter deposition or chemical vapor deposition, where silicon oxide can be deposited. We will get back to a more detailed explanation later on in the lecture. In this lecture, we will explore a wide range of topics to enhance your understanding of thermal oxide growth. We will not only go into process details and furnace layout, but also examine the theoretical model for the oxide growth. To help you determine the most suitable furnace at DTU Nanolab, we will also discuss oxide properties and how they are influenced by different process parameters. Silicon dioxide or SiO2 is grown on silicon wafers or samples in thermal oxidation furnaces. Oxidation processes can be divided into two methods: dry oxidation, where the oxygen gas reacts with silicon to form silicon dioxide, and wet oxidation, where water vapor reacts with silicon to form silicon dioxide. Hydrogen gas is produced as a byproduct. But what can thermal silicon dioxide be used for? Thermal oxidation is used in many different applications that surround us in our daily life, for example as structural layers in microsystem devices such as membranes, electrical insulating layers, protection layers for passivation or as hard masks, optical layers, sacrificial layers. A sacrificial is a material layer that is grown or deposited in one step of a process and then removed in a later step. Gate oxide layers for MOSFETs. A typical example for the application of thermal silicon dioxide in the electronic industry is the electrical insulation in MOSFETs, that is metal oxide semiconductor field effect transistors. A gate oxide layer, that is a thin less than 100 nanometers thick oxide layer, is located over the gate or active region of individual resistors. MOSFETs are the building blocks of logic operations in computer memory and processors. Furthermore, thermally grown silicon oxide is used as optical layers in the solar cell industry. In fact, solar cells represents an excellent example for a fabrication process that combines various thin film techniques like doping, for the light-absorbing layer, thermal oxidation, for anti-reflective and protection layers, and metal evaporation for electrical contacts. The color is the solar cell is related to the thickness of the oxide layer, and a dark blue solar cell reflects as little light as possible. This slide shows a drawing of the thermal oxidation furnaces in the cleanroom. The blue and gray background colors indicate that only the loading area can be accessed from cleanroom side, while most of the furnace is located in the service area. The furnace itself is an about 2 or 3 meter long, quartz tube, also called a furnace tube. So, why do you think that the furnace tube is made of quartz, even though it would be easier and cheaper to make it out of metal? Well, quartz is a very clean material. A furnace tube made of metal would contaminate wafers with metal. The metal would be incorporated into the grown oxide layers and thereby reduce the oxide quality. Furthermore, quartz can withstand very high temperatures, which are required for thermal oxidation. The glass transition temperature for quartz is about 1200 degrees, and the common oxidation temperature is between 800 and 1100 or 1150 degrees, depending on the furnace. Quartz also has a considerably smaller thermal expansion than most metals. The furnace is closed by a door on the cleanroom side. The gas inlets are placed at the back of the furnace tube. The following gases are available: nitrogen, which is used for annealing of the grown oxide films, as well as for purging to keep the furnace tube clean in between processes. Oxygen is used for dry oxidation, and water vapor is used for wet oxidation. The water vapor is generated by either a torch, a steamer, or a bubbler, and this will be explained on the next slide. At the door side, there is a so-called scavenger box with a gas outlet. The gas outlet is connected to cleanroom exhaust system. On the door, a cantilever is mounted. Wafers are placed in one or more quartz boats on the cantilever, depending on which furnace that is used. The furnace is heated by either 3 or 5 heating elements, depending on the size of the furnace tube. The heating elements are coils wrapped around the furnace tube. They are placed in the middle part of the furnace tube. Therefore, only a limited area in the center of the furnace tube will have a uniform and stable temperature. The quartz boat or boats with wafers should be placed here. For most oxidation furnaces available at DTU Nanolab, an arrow indicates where the boat has to be placed on the cantilever when it is loaded into the furnace, to be at the center position inside the furnace tube during the oxidation process. As explained before, wet oxidation requires water vapor or steam. The water vapor can be generated in different ways, by a torch, a steamer, or a bubbler. A torch is a small quartz chamber which is heated up to above 800 degrees, and then hydrogen and oxygen gases start to flow into the torch. Because of the high temperature, hydrogen ignites and burns oxygen into steam. The steam has a high purity and uniformity in terms of drop size. Unfortunately, the combination of explosive hydrogen and high temperatures require considerably interlocks and safety on the system. The second option is a steamer. A steamer is like a water boiler. It is a heater that generates steam from deionized water. The generated steam passes through a non-porous membrane to remove impurities. The steamer requires lower temperature than the torch and only deionized water. The steamer also generates a very high purity and uniform steam. The third option is a bubbler. A glass bubbler contains deionized water that is heated to near boiling point, and then a nitrogen or oxygen carrier gas is flushed through the bubbler and into the furnace together with the generated steam. A bubbler is the most simple and cheapest solution to produce water vapor, but the steam is less uniform and less clean. Furthermore, water needs to be added manually to the bubbler before an oxidation process is started. All three solutions are available at DTU Nanolab. The type of water vapor or steam generation technology determines the oxide quality, which might be important. It also slightly affects the wet oxidation rate. The oxidation furnaces are usually kept at a standby temperature of either 400 or 700 degrees. Silicon wafers are placed in one or more quartz boats, depending on the furnace, and the boats are loaded into the furnace without cooling it down. Once the temperature reaches the specified oxidation temperature, usually 800 to 1100 or 1150 degrees, oxidation gases, either oxygen or water vapor, are introduced into the furnace tube and the oxidation begins. Once the oxidation is completed, the furnace tube is purged with nitrogen to stop the oxidation reaction and to anneal the wafers. The annealing step improves the oxide density and thereby the quality of the oxide film. It can repair some defects within the crystal structure and reduce some vacancies and dislocations at the grain boundaries. A nitrogen annealing step is an inherent part of each thermal oxidation recipe at DTU Nanolab. An annealing time of 20 minutes is standard, but users are allowed to change the time. The annealing is done at the same temperature as the oxidation. Finally, the furnace will be cooled down to 700 degrees, and the wafers are unloaded. Some furnaces can be cooled down to a standby temperature of 400 degrees to save energy. Some typical process parameters include a gas flow between 1 and 5 SLM or standard liters per minute, and an oxidation temperature between 800 and 1100 or 1150 degrees. Since the oxidation process takes place at atmospheric pressure, no vacuum pumps are required. The gases are introduced into the furnace tube through mass flow controllers that control the gas flows. The gases are removed by the cleanroom exhaust system through the scavenger box. The furnaces at DTU Nanolab have several fixed recipes for both wet and dry oxidation, for example wet 1000 for wet oxidation at 1000 degrees or dry 1100 for dry oxidation at 1100 degrees. Users can only change the oxidation time to change the thickness of the grown oxide layer. As mentioned before, thermal oxidation can be divided into two methods, dry oxidation and wet oxidation. In a dry oxidation process, oxygen reacts with silicon to form silicon dioxide. This type of silicon dioxide is very dense and amorphous. This means that a very high-quality oxide film with very few defects is grown. But unfortunately, the oxidation rate is quite low as will be explained later in this presentation. At DTU Nanolab, users are normally only allowed to grow up to 300 nanometers of dry oxide. If a thicker oxide layers is required, a wet oxidation should be done instead. In a wet oxidation process, water vapor reacts with silicon to form silicon dioxide. While wet oxide has a high quality too, it is less dense than a dry oxide. Wet oxide layers grow considerably faster than dry oxide layers. For a better understanding, the growth of 3 micrometers of wet oxide requires about 23 hours at 1100 degrees. At DTU Nanolab, users are normally allowed to grow up to about 3 micrometers of wet oxide. If you need a thicker oxide layer, please contact the thin film group, or buy wafers with an already grown oxide layer. But why do dry oxide layers have a better quality than wet oxide layers? Well, some hydrogen molecules are incorporated into wet oxide films, causing imperfections in a less dense film, thereby creating oxide films of lower quality. Let's have a closer look at the properties of the thermal oxidation process. Thermal oxidation is a growth method, not a deposition method like the other thin film techniques that are explained in the PVD, CVD and ALD thin film presentations. Silicon dioxide is grown, not deposited, on silicon samples. All accessible silicon surfaces are oxidized, also the wafer backside. Silicon oxide is always formed at the silicon surface, that is at the interface between the silicon surface and the silicon oxide layer. This means that oxygen or water vapor molecules need to diffuse through the already formed silicon oxide layer to reach the silicon surface. On the silicon surface, the oxygen or water vapor molecules react with the silicon atoms, creating a new layer of silicon oxide between the silicon and the existing silicon oxide surface. In this way, the silicon oxide layer grows from the silicon surface and upwards. The advantage is that any contamination on the silicon wafer will ultimately remain on the surface, leaving the grown silicon oxide layer very clean. Thermal oxide has an amorphous or porous crystal structure, where about 45% of the space is occupied by silicon oxide molecules. Atoms are sitting randomly in the crystal lattice, in opposite to quartz, which has a very well-defined and dense crystal structure. A transmission electron microscopy image can be used to look at the crystal structure of the silicon-silicon oxide interface, as shown in the right-hand image. It shows that while most silicon oxide is amorphous, a more crystalline structure can be observed very close to the interface to silicon. During the thermal oxidation reaction, silicon is consumed, while oxygen is added, and the silicon oxide layer is growing. In total, the thickness of the silicon layer that is being consumed equals 45% of the thickness of the oxide layer that is being grown. The remaining 55% are accounted to added oxygen and the fact that silicon oxide molecules are significantly larger than the individual silicon atoms that they replace. From that, the expansion factor alpha can be calculated. Alpha is 1.2. Alpha allows an easy calculation of the added layer thickness, which can be useful, for example, to determine how much a groove or microchannel will shrink after oxidation. For example, a 10 micrometers wide channel will shrink to become 7.84 micrometers wide after growth of 2 micrometers silicon oxide. The calculation can be seen on the slide. Remember that thermal oxide is grown on all available silicon surfaces, also on the bottom and side walls on structures and on the front and back side of the wafers. Thermal oxide grown on silicon has a compressive stress in nature. This arises primarily due to two main factors. Firstly, volume expansion. The volume occupied by a silicon atom is significantly smaller than the volume occupied by the equivalent amount of silicon in the form of silicon dioxide. This volume can only expand upwards, and this volume expansion leads to a compressive stress in the oxide layer. And secondly, lattice mismatch. Silicon has a diamond cubic crystal structure, while silicon dioxide has an amorphous crystal structure. This difference in crystal structure leads to lattice mismatch between the silicon substrate and the growing oxide layer. To accommodate this mismatch, the oxide layer experiences compressive strain, contributing to the overall compressive stress. The consequence of the compressive stress can cause wafer bowing, stress-induced defects, or reduced device performance. Be aware of that the stress will cancel out when oxide is grown on both sides of a wafer. A silicon nitride layer with a tensile stress can also be deposited on the oxide layer to reduce the stress. So, what do you think? Is the growth rate for thermal silicon oxide linear or nonlinear as a function of time? Even if one would intuitionally assume that the reaction is nonlinear, there is not a simple answer to the question. The growth rate for very thin silicon oxide layers, up to about some hundreds of nanometers, is linear. But as the silicon oxide layer grows thicker, the growth rate will decrease with time and nonlinear. The reason for that is as follows. As the silicon oxide layer grows and becomes thicker, it takes increasingly longer for the oxygen or water vapor molecules to diffuse through the already grown silicon oxide layer and reach the silicon surface. To fully comprehend the oxidation process, it is important to grasp the kinetics of oxide growth. This involves understanding how water vapor or oxygen molecules are transported through the existing silicon oxide layer to reach the silicon surface and react with the silicon atoms there. To simplify matters, oxygen and water molecules are from now on collectively addressed as oxidants. The growth of thermal silicon oxide can be predicted using a mathematical model, called the Deal-Grove model. It was invented by Bruce Deal and Andrew Grove of Fairchild Semiconductor, published in 1965. It laid the foundation for understanding and predicting thermal oxidation of silicon, fundamental for semiconductor manufacturing. The model considers three primary steps. Firstly, diffusion of the oxidants from the bulk gas, that is the gas stream in the furnace, to the outer oxide surface, the gas-silicon oxide interface. Secondly, diffusion of the oxidants through the existing oxide layer to the silicon-silicon oxide interface. Thirdly, reaction of the oxidants with the silicon atoms at the silicon surface. Three fluxes are associated with the oxidation process. A flux is measured as the number of molecules per time per area and is thus representing the flow rate. The flux F1 of oxidants in the gas stream is governed by local concentration differences of oxidants between the gas stream and the silicon oxide interface. The flux F2 of oxidants through the existing silicon oxide layer is governed by diffusion due to a concentration gradient towards the silicon oxide-silicon interface. The flux F3 is related to the reaction between the oxidants and the silicon atoms at the silicon surface and is governed by the reaction rate of the oxidants. In steady-state condition, meaning, looking at a system that is unchanged in time, all three fluxes are equal, and the oxidation can be mathematically expressed as follows. X squared plus A times X equals B times T plus tau, where X is the oxide thickness. A and B are constants related to the diffusion and reaction processes. T is the oxidation time, and tau is a constant related to the initial oxide thickness. Tau can be ignored for new or blank silicon wafers without any native oxide present on the sample surface. This equation is called the linear parabolic Deal-Grove equation. It predicts the oxide growth very precisely with two regimes, a linear regime at the beginning of the oxidation process, and a parabolic regime, where the diffusion becomes the limiting factor for the oxidation rate, as also shortly discussed before.
Solving the Deal-Grove equation for the oxidation time against zero, or against infinity, the oxide thickness can be calculated using the following equations. At the beginning of the oxidation process, the oxide growth rate is constant, and the oxide thickness X is linearly proportional to time. This is dominated by the reaction-limited process, meaning that the oxidation rate is limited by how fast the oxidants can react with the silicon atoms. Flux F3 is the limiting factor. So, for short oxidation times, the oxide thickness X equals B divided by A times the oxidation time T. B over A is called the linear rate constant. As the oxide layer thickness increases, diffusion becomes the limiting factor for the oxidation rate, and the oxide growth rate slows down, following a parabolic relationship with time. This means that the oxidation rate is limited by the diffusion of oxidants through the existing silicon oxide layer, which takes increasingly longer the thicker the oxide layer is. Flux F2 is the limiting factor. So, for long oxidation times, the oxide thickness X equals the square root of B times the oxidation time T. B is called the parabolic rate constant. The flux F1 is never a limiting factor, because there are more than enough oxidants in the gas stream in the furnace. The A1 furnace, also called the boron drive-in and pre-dep furnace, has been installed in the clean room at DTU Nanolab for almost 30 years. Through these years, users have grown a tremendous amount of silicon oxide, and lots of experimental data has been collected over time. From this data, it is clearly visible that the oxide growth rate follow the theory of Deal and Grove quite well. The only exception is the wet oxidation done at 950 degrees, which unfortunately contains some wrong measurements. The following graphs show the linear and parabolic rate constant as function of oxidation temperature. The blue curves in the graphs are for wet oxidation, and the red curves are for dry oxidation. From the two graphs it can be seen that both the linear and the parabolic rate constant increase with temperature. This means that the oxidation rate for both wet and dry oxidation is dependent on the temperature. The higher the temperature is, the faster the oxidation rate is. This also means that for a given time, the higher the temperature, the thicker the oxide layer that is grown. Furthermore, the linear as well as the parabolic rate constant is larger for wet oxidation compared to the dry oxidation. This means that wet oxide layers grow faster than dry oxide layers. The difference is caused by the different molecule size of the oxidants used in the two processes. Water molecules form hydroxide or OH- molecules which are smaller than the oxygen molecules used in dry oxidation. They diffuse considerably faster through the existing silicon oxide. The Deal-Grove model has been instrumental in understanding and predicting thermal oxide growth as function of time. But it has some limitations that the user needs to be aware of. The limitations are related to very thin layers, polycrystalline silicon, dopant effects, stress and strain, and temperature and pressure dependence. For very thin layers, the model struggles to accurately predict the oxide growth during the initial stages, especially for oxide thicknesses below 30 nanometers. This is because the model assumes a linear growth, but in fact very thin oxides grow nonlinear and faster than the model predicts. The model is primarily developed for single crystal silicon and its application to polycrystalline silicon is limited. The varying crystal orientations and the presence of grain boundaries affect the diffusion and reaction kinetics, which makes it difficult to choose a value for the linear rate constant. Because oxidants can diffuse rapidly along grain boundaries, polycrystalline silicon oxidizes faster than single crystal silicon. The model assumes a pure silicon substrate. However, the presence of dopants, such as boron or phosphorus, can influence the oxidation rate. These effects are not explicitly accounted for in the model. Heavily doped silicon wafers might be oxidized faster than the model predicts. More information on that will follow later. Furthermore, the model does not consider the stress and strain induced during oxide growth, which can affect the diffusion rates and reaction kinetics and thus the oxidation rate. Finally, the Deal-Grove model considers temperature dependence through the constants A and B. It also assumes that thermal oxidations are done at atmospheric pressure. But in the practice, there might be a little overpressure in the furnace, and this will increase the oxidation rate. However, the Deal-Grove model might not accurately capture the complex temperature and pressure effects on the oxidation process, especially at extreme conditions. Despite these limitations, the Deal-Grove model remains a valuable tool for understanding the fundamental principles of thermal oxidation. More complex models have been developed to address some of these shortcomings, but the Deal-Grove model still provides a solid foundation for analysis and process optimization. A high-quality silicon oxide is characterized by several key properties. A high density, a low defect density, that means minimal defects such as pinholes and particles. A uniform thickness, a high dielectric strength, meaning the ability to withstand high electric fields without breaking through the silicon oxide layer. The oxide quality widely depends on the cleanliness of the furnace and the samples used. Even a small amount of impurities will negatively affect the grown oxide quality. While some contaminants will grow with the oxidation and remain on the outside of the oxide layers, others are incorporated into the grown oxide film. For example, impurities, like sodium or potassium or metal ions, can diffuse through the oxide layer and heavily reduce the oxide quality. Depending on the application, this can render samples to be useless. The oxide quality can be estimated by measuring the breakdown voltage. It is a destructive and time-consuming test that requires dedicated test samples to be made, and the measurement tool belongs to DTU HealthTech. It is also possible to measure the lifetime of the silicon oxide. We will not go into details about breakdown voltage and lifetime measurements in this presentation. To assure a high oxide quality, contaminations on the samples and in furnaces must be reduced. Therefore, samples often need to be specially cleaned with an RCA treatment. It is a standard cleaning process used in semiconductor manufacturing. It removes organic and inorganic contaminants and native oxide from the surface of silicon wafers before high-temperature processing steps. The process was developed by Werner Kern, while he was working at RCA, the Radio Corporation of America, in the 1960s. The RCA cleaning typically involves two main steps. The first step removes organic contaminants using a mixture of deionized water, ammonium hydroxide, and hydrogen peroxide. The second step removes metallic and ionic contaminants using a mixture of deionized water, hydrochloric acid, and hydrogen peroxide. Normally, An intermediate cleaning step that etches away native oxide using hydrofluoric acid also has to be done. This can, however, be skipped if the wafers already have a grown or deposited oxide layer that should not be etched away. Notice that wafers normally have to be RCA cleaned and go into a furnace on the same day. To reduce cross-contamination of the furnaces from other cleanroom fabrication processes or tools, users at DTU Nanolab are required to check what materials that are allowed in the furnaces and what materials that might be added in other process steps and possibly can contaminate the furnaces. This can be done by checking the cross-contamination sheets in Lab Manager. Before you use a furnace, you should always check the cross-contamination sheets for it. And please contact the furnace responsible persons if you are in doubt of whether your wafers are allowed in a furnace or not. For instance, the stack furnaces are oxidation and doping furnaces. They are some of the cleanest tools available in the cleanroom. Only clean silicon wafers are allowed in these furnaces. In the notes section of the cross-contamination sheet, more detailed information can be found, stating that all wafers, including new silicon wafers, processed wafers, test wafers, and dummy wafers must be RCA cleaned in order to be allowed in these furnaces. RCA cleaned wafers have to be stored in dedicated RCA transfer boxes. Other wafers like new wafers that have to go into a furnace, for which RCA cleaning is not required, have to be stored in dedicated furnace transfer boxes or clean boxes from new wafers. Do not store wafers for the furnace in boxes from the cleanroom entrance. Also, please note that wafers for the oxidation furnaces should only be handled with the dedicated tweezers which can be found by the wafer cabinet in cleanroom B1, by the RCA bench, and by each furnace. Oxidation of structured silicon samples shows commonly a variation in the oxide growth rate. The oxidation rate is smaller around edges compared to flat areas, and there are some variations between sidewalls and bottom or top surfaces. The picture shows S cross-sectional SEM-image ODA cleaved silicon wafer after thermal oxidation. The corners of the structures clearly show some variation in the oxide thickness. There are less silicon atoms for oxidation available on corners compared to flat areas as two sides share each atom. That causes a rounding of corners compared to flat area. This phenomenon can both a disadvantage and a nice feature. For example, microstructures that have been etched by a plasma etcher using a specific process called a Bosch process develop so-called scallops. This is due to an alternation between passivation and etching steps that allows etching of deeper features. This alternating causes sidewall scallops, as can be seen on right image, and they are mostly unwanted. Thermal oxidation can be used to reduce or even remove scallops completely. After the structures have been etched, they are partially oxidized. The oxide is then etched away using hydrofluoric acid. As hydrofluoric acid has an extremely low etch rate for silicon compared to silicon oxide, mostly oxide is removed, leaving clean and smooth sidewalls. However, depending on the application, for example if sharp features are required, the rounding of corners can also be a disadvantage. Be aware of that very small structures, for example narrow pillars or lines, as shown in the right SEM image, are easily oxidized completely. If the oxide is then etched away in hydrofluoric acid, the structures will mostly disappear. Coming back to the left picture. As mentioned before, the oxide thickness on the sidewalls is visibly larger than on the bottom of the structures. This is caused by a difference in oxidation rate depending on the orientation of the crystal plane. It is an oxidized C1O sample, so the top and bottom structures are on the 1O crystal plane, and the sidewalls are on the 1O crystal plane. As can be seen, silicon is faster oxidized in the 1O than in the 1O crystal plane. In the linear regime, the oxidation rate is determined by the reaction rate which depends on the number of silicon surface atoms available for the oxidation reaction. For example, on the 1 crystal plane, silicon has more atoms available than on the 1O crystal plane, thus the 1 crystal plane oxidizes faster. In the diffusion limited regime, this phenomenon can be almost neglected as the time the oxidants need to diffuse to available silicon atoms is longer than the actual reaction time. The Deal-Grove model describes the oxidation growth on the 1O crystal plane. For the other crystal planes, the linear growth rate constant needs to be multiplied with 1.68 for the 1 crystal plane, and with 1.45 for the 1,1,0 crystal plane. At DTU Nanolab, we are mostly working with silicon 1,0,0 wafers, where the surface is a 1,0,0 crystal plane. As users are required to measure the thickness of the grown oxide layer on the surface of a silicon test wafer, measurement results shown in the process logs in Lab Manager are always representing the thickness measured on silicon 1,0,0 wafers. The growth rate can be influenced by N-type and P-type doping of silicon with generally faster oxidation rates than the Deal-Grove model predicts. N-type doping with phosphorus increases the oxide growth rate, but only in the reaction-limited regime. Phosphorus creates defects in the silicon crystal which form diffusion paths for oxygen or water vapor. Furthermore, phosphorus atoms at the silicon oxide interface can catalyze the reaction between the silicon atoms and other oxidants, thus increasing the oxidation rate. However, while phosphorus doping generally increases the oxidation rate, the exact impact can vary depending on factors such as doping concentration, oxidation temperature, and ambient conditions. Additionally, excessive phosphorus doping can lead to other effects, such as oxide quality degradation. P-type doping with boron increases the oxide growth rate as well, but for different reasons. The presence of boron converts grown silicon oxide into boron silicate glass, that is boron-doped silicon oxide. The lattice constant in that type of silicon oxide is restrained, which makes it easier for oxidants to diffuse through it, resulting in an increased oxidation rate. The effect of boron doping on the oxidation rate is generally smaller than that of phosphorus doping and can be influenced by factors such as doping concentration and oxidation conditions. Knowing how to estimate an oxidation time is probably the most important practical information for you. So, how do you decide what oxidation time is required to grow an oxide layer with a certain thickness on your silicon wafers? Well, there are various options available. Look up measurements from other users in the process logs available in Lab Manager. As mentioned before, the repeatability is very good. Look up the oxidation curves for common oxidation processes at DTU Nanolab by the furnaces or in Lab Advisor. It is also possible to use one of the many available online oxide thickness or oxidation time calculators. For example, the calculator made by UltraMems. It will not give a 100% precise oxidation time, but a good starting point. The UltraMems calculator is currently quite precise for the furnaces in the clean room at DTU Nanolab. At DTU Nanolab, oxidation times are limited to prolong the lifetime of the quartz tubes and to avoid excessive long bookings of the furnaces. As mentioned before, the glass transition temperature for quartz is about 1200 degrees, very close to the highest oxidation temperatures. In most furnaces, wet oxidation can be done at 1100 degrees for up to 23 hours. This results in approximately 3 micrometers of thermal oxide. In some furnaces, the A-stack furnaces and the C3 and C4 furnaces, oxidation can be done at 1150 degrees, but for only 8 hours. It is normally not allowed to oxidize the same wafers more than once. If a thicker oxide layer than 3 micrometers is needed, the wafers should be bought externally, or it might be an option to deposit, for instance, PECVD oxide on the wafers instead of doing a thermal oxidation. The silicon oxide thickness can be measured with various techniques. The easiest and maybe most precise method is to do an optical measurement using an ellipsometer or a spectrometer. At DTU Nanolab, both methods are available. In Lab Manager, the ellipsometer is called ellipsometer vase, and the spectrometer is called FilmTech. You can also cleave a wafer and look at the cross-section in a scanning electron microscope. In case you have structures on your wafer that would interfere with an optical measurement, this is a good method to check the oxide thickness. But simply using your eyes to determine the oxide thickness is a viable method, too. Though it has some limitations. The human eye can tell the color difference between 2 silicon oxide layers with a thickness difference of only 10 nanometers. Silicon oxide is mostly transparent while silicon reflects a large spectrum of the incident light. On an oxidized silicon wafers, some of the incident light is reflected at the top of the silicon oxide layer and the remaining at the silicon oxide-silicon interface. The interference pattern of the reflected light results in a certain color dependent on the oxide thickness. The following chart shows the relationship between the oxide thickness and its respective color. The same colors are visible on the rainbow-colored silicon wafer. Each color presents a different silicon oxide thickness. A color thickness chart can be found by the furnaces inside the cleanroom. Let's round up the lecture with a presentation of the oxidation furnaces available at DTU Nanolab. As explained previously, only the loading area is accessible common area, while the actual furnace, including furnace tube and gas lines, is located in the service area. The following oxidation furnaces are available at DTU Nanolab. The A-stack furnaces. They are the cleanest furnaces available. Furnace A1 allows wet and dry oxidation of P-type silicon wafers at temperatures up to 1150 degrees. Water vapor is generated using a torch. The furnace is also used for doping with boron. Furnace A2 allows dry oxidation of very clean silicon wafers at temperatures up to 1150 degrees. Furnace A3 allows wet and dry oxidation of N-type silicon wafers at temperatures up to 1150 degrees. Water vapor is generated using a torch. Furnace A4 is not an oxidation furnace, it is solely used for doping with phosphorus. The C-stack furnaces. Furnace C1 allows wet and dry oxidation of P and N-type silicon wafers at temperatures of up to 1100 degrees. Water vapor is generated using a steamer. Furnace C2 is not an oxidation furnace, it is at the moment being used for annealing tests of samples with some metals. Furnace C3 allows wet and dry oxidation of P and N-type silicon wafers at temperatures up to 1150 degrees. In this furnace, small samples and wafer pieces are allowed with special permission, as the loading procedure is a little tricky. Water vapor is generated using a bubbler that can contain water for up to 8 hours wet oxidation. Furnace C4 allows dry oxidation of P and N-type silicon wafers at temperatures up to 1150 degrees. In this furnace, wafers with aluminum oxide and titanium oxide are allowed, and small samples and wafer pieces are allowed with special permission, as the loading procedure is a little tricky. All C-stack furnaces can also be used for annealing with nitrogen. The E-stack furnaces. Furnace E1 is the newest and biggest oxidation furnace in the cleanroom. It allows wet and dry oxidation of P and N-type silicon wafers at temperatures up to 1100 degrees. Water vapor is generated using a steamer. The furnace can also be used for annealing with nitrogen. The furnaces E2 and E3 are not oxidation furnaces. They are used for LPCVD deposition of silicon and silicon nitride, respectively. The A-stack and C-stack furnace all have space for 1 quartz boats with up to 30 wafers. 4 wafers can be oxidized in all these furnaces. In the C1 furnaces, 6-inch wafers can also be oxidized, because this furnace has been upgraded with a larger furnace tube. The E1 furnace has space for 2 quartz boats with 25 wafers in each boat, so up to 50 wafers in total. In this furnace, 6-inch and 8-inch wafers can be oxidized, but normally not 4-inch wafers. Remember that a test wafer should always be included in the boat, so the thickness of the grown oxide layer can be measured. It is also recommended to include some dummy wafers to improve the uniformity of the grown oxide layer. Smaller samples are allowed in the C3 and C4 furnaces with special permission. The uniformity of the grown oxide layer is very good, with a variation of less than 1.5% measured over 34-inch wafers in the A1 and A3 furnaces and over 56-inch wafers in the E1 furnace. Finally, if you have any questions regarding thermal oxidation or the oxidation furnaces, you are welcome to contact the Thin Film Group. The following Nanolab staff members are responsible for the furnaces: Panil or Patama on the process side, and Fleming on the technical service side. This material has been compiled as part of DTU Nanolab's initiative to provide our users with a deeper understanding of the theoretical principles behind our cleanroom equipment.